Yeah, so today is the last class of this course, formal class, where we have sort of covered the syllabus that I typically teach for this. Today is something that is a bit extra. It is a requirement, I feel, still, because I think all of you know that the whole course, we had designed with a particular problem in mind. That is how to, optically confine a trap particle, a microparticle or a nanoparticle, a mesoscopic particle, as we say. And so let me start sharing my screen. So the quandary here is one of the presentations, I think Anisha's group, that presentation is on this subject. So it is not fair that I dwell too much on it, because that makes their task somewhat easier. So what I will do today is give you a very basic picture of how things work. Of course, if you have questions, we can discuss, but the details and the broader picture will be given in the presentation, hopefully by Anisha and her partner. Okay, so let me start by presenting the screen. Yeah, so can you see? So this is
Yes, sir.
the good old picture that we had. We want to optically trap a particle in this sample chamber. We start with a laser here and a laser here. So they are two different lasers. So one of them we use as the trapping laser, which is actually this one. I had drawn this one here, but this is actually not so much for trapping. I mean, later on I realized that the trapping laser is actually this one. But then, so the reason that this is the trapping laser is basically because I have this object. This is an acoustoptic modulator, and the job of this is essentially to scan the beam. So as you know that acoustoptic modulators work on, so they have a phase grating inside. So there is this crystal, there is this small crystal which is sensitive to acoustic waves of very high frequency. This is like RF radio frequencies of like hundreds of megahertz or gigahertz, and that creates diffraction grating. So essentially, a charge, a reorientation of refractive index of the refractive index inside the crystal. So people who have done the Ramannath experiment have done this in the case of water. So this is just the solid state manifestation of the same principle. And what you get is a phase grating, as I said, that leads to diffraction. So you actually get a zero spot, which is an unshifted spot here, beam. And along with that, you also get a first order shifted beam, which is like either +1 or -1. Of course, along with the spatial shift, you also get a frequency shift. So that we do not utilize here. But as you can well understand, that I can do all kinds of things. I can, in principle, give, so if I, depending on the RF signal that you give to the acoustoptic modulator, you can change the grating characteristics. And, if you give a very, so every acoustoptic modulator has a range of frequencies in which it works. So suppose this particular one that we have, it has the highest efficiency at 133 megahertz, but it works between 100, about 100 to 160. So you will actually get different frequency shift from the laser actual zero frequency and the spatial shift. So for example, if I give 160 megahertz, this beam will shift more. If I give 100 megahertz, it will shift less. So for example, if I actually scan the RF, which is nothing but some kind of a, you give a sine wave or something, and I scan the amplitude of that, I can, so yeah, I can change, sorry, I scan the frequency of that. So that basically will, actually it's not the frequency, it's the amplitude that you scan. Yeah, so the amplitude, the thing inside is designed in such a way that depending on the voltage that you give, you can actually change the efficiency of the acoustoptic modulator. And you can change the pitch as well. So I can basically scan this first order beam spatially, and if I put a square wave, for example, then I can in principle even use this as a switch. So I can switch between the first order being present and absent. So what I can do is I can so this with the single laser beam and this acoustic modulator, I can actually create two traps. So this is coupled in through these optics inside this chamber. There's a whole thing I could have done here as well. So in principle, I can use this laser to trap as well. So that's not a problem. The only thing that we use this as a detection laser. So the reason that we call this, I mean, this is somewhat different, is the power level of this is kept much lesser, so that it does not go and influence the particle that is trapped. So as we said, as we described in the entire course, so all of these have their own functionalities. So the lens system here basically changes the beam diameter, because why do we need a large diameter? Because we actually need to maximize the intensity of the laser beam inside the sample chamber, and that is what we're going to discuss. So this intensity, why that is important. So that is just the picture that I want to give to you. So the higher the intensity, the greater is the trapping force, and so that all the different stages that lead to this beam finally being sort of focused inside the trap is what we have actually included in the course. Things like, this is a polarizing beam splitter, so, and this is a half wave plate, so these are made of birefringent materials and isotropic media. So these are able to change the the polarization of this light, linear polarization. Of course, these are linear polarized light, this and this both, and with the combination of this and that, this is a polarizing beam splitter. The transmitted beam is p polarized, the reflected beam is s polarized. So if I actually give a combination of p and s, I can change the intensities of power or intensity, whatever you say, of the beam in this direction. So this is a great control of a continuous control of power that one can actually design for lasers. So if it's a polarized laser, a combination of half wave plate and polarizing beam splitter can actually give you an extremely good changeable. It's like a tunable neutral sort of a. So in optics we have these things called neutral density filters. So if you want to change the power of laser light, so you essentially put that. Those are like absorbing filters. So but those are fixed. So those are like the ones that have very very high optical density. Those like very, like it's a like 10 to the power 4 times attenuation it'll give you. So you barely, if you just put it to your eye, you cannot see anything. So at times we need those as well. However, those are discrete, so different filters will give you different attenuation, whereas here you will actually get continuous attenuation using this. So but that also is a property of polarization. So we have learned how deal with polarized light, how you quantify it, measure it by the Jones-Muller, by Jones-Stokes, Stokes-Muller Jones matrices, and then of course you have this is a metal, these are metallic mirrors, so these are lenses, dielectric objects. So how dielectric light interacts with the dielectric objects, and how it interacts with metallic objects, that also we have studied. And finally, as we said here, this microscope objective focuses the light inside the spot, and as we learned recently, that the focal spot size depends entirely on the input diameter of the beam. So it is very important that this microscope, the back aperture of this microscope, is filled by the beam. So the beam size has to be as big as that. In fact, we slightly increase. It's called overfilling, so that's a detail. But that sort of ensures that you get maximum. This focal spot of this, focal spot here is minimum, because that ensures that the intensity is maximum. So this is the experimental design that we finally converge on, how you trap a particle. And that, of course, means that when you're trapping a particle, means you are employing some kind of a restoring force, right? So light has to essentially uh, uh, employ some force. It has to exert force on a particle, right? And that, how do you think that can happen? When can light sort of exert force? Let us start the discussion. Yeah, when can what is the physics of light exerting force? Yeah. How can light induce force on matter?
When the matter's momentum is comparable to the momentum imparted by the light or something like that.
Matter's momentum. What is the meaning of matter's momentum? You need to have a momentum of the matter, is it?
No, no, I think he says like the momentum that a photon has, if
Oh,
that is
that.
enough,
Oh, okay.
that is
That
enough to
is
do
like a.
some disturbance.
But that is like a quantum. I'm talking about bigger particles, right? Much bigger. These are like classical, micron-sized particles. So, what is the mechanism of light exerting on any kind of force on big particles? I mean, that is what he was talking about. Is when you have particles which are, comparable to, the photon. I mean, where of course you know that light has h nu and all that, and if you have a particle which is going to feel force, that is fine. But say a dust particle, right, which is few tens of microns. So what makes light interact with that, with those? Hmm? What is the mechanism?
Light can scatter, like that's what we have done till now. Like light,
What
light
is the
can deflect
mechanism?
off it.
Scatter,
Oh,
scatter, mane, what is that you want it to be? Well, what is, how does it work then? I mean, that is something. So force acts on what?
So there can be a like electric field which imparts the like
To what?
electro
I
the
mean, you
dipoles, right?
exactly, yeah. So these are things you have to immediately answer. No, unless you have a dipole, there is no chance of force, right? So essentially, the field interacts with the dipole, right? So there has to be induced dipole. So it is only those materials which are polarizable, only those are essentially stuff that can be trapped. If you do not have any polarizability at the wavelength that you are employing, you cannot trap a particle because the light will not exert any force. So the first thing that we study, therefore, it is I'll just write me basics of optical trapping. First thing that we try to say is, so a dipole, sorry, light induces a dipole moment in a particle which has a finite polarizability at the light wavelength. This is critical. This is the basics of everything. So, so I can tell you that a very experienced person in optical traps was quite befuddled. So he had come to ISER to give a talk on these kind of things. And I think some student asked, how on earth are gold, no, so I mean, metal particles, metal microparticles, the nanoparticles is problem, but nanoparticles are routinely trapped. So he was asked, like, how on earth are metal nanoparticles trapped? So what is, because typically we think that, light basically is like metals reflect, right? That is what the basic, very general understanding is. So he was actually quite befuddled. He could not answer at the first, he could not answer the question. Actually, we answered. So what do you think is the answer? So I'm saying that even metal nanoparticles can be trapped. Gold or silver can be trapped, which we know that. So what do you think is the reason? I mean, what
Sir,
do you
I
need?
think the radiation pressure can also be used as a
No,
force.
no, no. Radiation pressure in this case, no. Radiation pressure does not. Radiation pressure force acts. It's a destabilizing force. It actually acts as we see. So it is. It acts in the direction of the light. So it pushes the light out. So it is not confining.
Okay,
Okay, it is not
okay.
confining. And that you can understand, right? Sorry?
Eddy current, maybe.
Eddy current? No, no, think of, no, I think you're not thinking in the right direction, in the sense that metals, think of how metals interact with light, right? We've covered this. How do metals interact with light?
There is absorption.
Yeah, so,
Matter.
but then, yeah, think of, the whole point is this, note this line, note this line. Finite polarizability at the light wavelength. So then, you did that exercise, right? Where you found out the optical constants of metals.
Yes, sir.
So
what,
then,
how is that related to this?
Okay,
think,
so
no,
at
what did you,
certain wavelength, it would behave, I mean, not
behave
like
as?
yeah, the like, dielectric materials.
Exactly. What, guys, तुम लोग homework करते हो, सोचना होगा ना. That is basically the, so you remember the curve, right? Metal का जो curve था, that thing is like it goes, I think if I remember, reflectivity basically कुछ, I mean if you
Okay.
look at real and imaginary component था ना metal का, वो ऐसा जाके ऐसा करके जाता है, right? Real part and the complex, the imaginary part वो उल्टा जाता है, right? वो कोई ऐसा जाके it sort of increases like this. So this region is where this is like lambda if I keep on increasing, where the real part is high, that is where it behaves absolutely like a dielectric. And that means it has finite polarizability. Okay, so these are, so see again, please guys, if you do not get out of this notion that metals are very high reflecting, please get out. Then if you do not get out of that, then the whole purpose of this course is defeated. As I said, light has a huge, spectrum, and properties of objects are completely dependent on what wavelength you're using in order to study them. So I'm not blaming you, because this was a senior researcher who has a well-established lab. He also could not, he was stumped. But that basically means that, he had forgotten his basics or whatever. But you have just been taught, right? So you have just learned this. So get this into your head that every object will behave differently depending on the wavelength at which you are asking questions of it. If of course you go and use a IR 900 800 nanometer beam to trap, it'll all be radiation pressure force. It will not, so we will study now, there's no gradient force at all. But at lower wavelengths, you can actually get extremely good trapping with metallic particles as well, because metals basically will act as dielectrics. So please understand that, remember that. Okay, so essentially it's a matter of force on dipole. So the first one that what we shall study or just look at is force on a dipole in a uniform electric field. Okay, so intuitively, what do you think this will be? What do you think it will be? So I'll put there's a figure. I will put this. Oh, by the way, so the reference for this, I'll tell you. Let me put the figure. So this is what we have. This is an uniform electric field lines. So you have the dipole, positive, negative. So the force on this charge is QE, and this one is minus QE. So what will the force be on this dipole?
So there will be a torque, right?
Yes, correct. So but the force is?
Force is 0.
Yes, absolutely. The force, sorry. So basically force is nothing but F plus F minus equals just QE minus QE, that is 0. But the torque is not 0, as Rohan said. That is very clearly because this is like L by 2 cross F plus minus L by 2 cross F minus, and that is clearly, if you just write this, I'm just jumping this step, so it is QL cross E, and that is essentially P cross E. This is fine. Right, so yes, there is torque, there is no force. Okay, Acha, by the way, the reference, I think this is, I would refer to, this is the book, that chapter that we have. So this is like the book, Ghosh and Banerjee. This is chapter 13. There is another book on optical tweezers. Just on that's a very sort of, the whole book is on that, optical tweezers by, I don't remember the first author. It is, I think, by Marago and Volpe, Giovanni Volpe. Wait just a second. I think, and we need to tell you whether that is by 3 authors. Let me just, give me a second. Yeah, Philip Jones. Okay. Yeah. Marago, Volpe, and Jones. This also you can look at. Okay. So yeah. So this is fine. The next question would obviously be, if you think of, well, the next thing that we will get to is force. I should put in torque. That is essentially force and torque in a non-uniform electric field. So that is actually, you can quite easily understand that is not going to be zero, right? So this is the whole premise of optical traps. The fact that the force, essentially the force is what we typically look at. The torque is more complicated because we normally use spherical particles to trap, because asymmetric particles are, there's a lot of problems because the torque can be destabilizing as well. But the fact that the force is non-zero on dipoles in a non-uniform electric field is at the heart of optical trapping, because that tells you that you can actually design beams which are non-uniform, which are inhomogeneous in their intensity distribution, and that basically leads to torque trapping. And so why this is non-zero is quite simple. You just see that if I write down the expression for force, that is nothing but EQE at R plus L minus E at R, and if I now sort of write this, just break this out in different units, in the sense, if I go in terms of X, Y, and Z, then it becomes easier. Then you can directly look at it simply. So we just write this as Q, the component wise. So this is like EX, X plus DX, Y plus DY, and Z plus DZ. Sorry, I should not DX. Sorry, it's LX. Z plus LZ minus EX. So I'm looking at the X component, say. So if I'm just looking at the X component part, EX, X, Y, Z, right? So that would essentially mean that if I do a Taylor expansion now, this is just Ex, XYZ plus LX del EX del X plus Ly del EX del Y plus LZ del EX del EX del Z minus EX XYZ, and so clearly from here you can see that this one cancels off. So what you finally get, if I now adding all three components, what you basically get is this. Yeah, so in fact, if I, so basically this will be nothing but fx is q dot del of ex, sorry, q dot e, so it's not q dot, sorry, q, what am I writing? Q ex dot del ex, right? Which means that finally your f is nothing but QE, which is nothing but P dot del E, right? This is a very, very important expression. This is what we do. So this is clear, very simple, right? This is completely simple. I think yeah, so you should not write adding all components. Adding all components you get is not correct. What is this?
Actually, sir, there will be a bracket, no? Otherwise, it is not going to a vector.
Yeah, so they are, yeah, of course. Yes. Okay.
That P dot del will be a vector, right, sir?
Yeah.
And
So
E will be
P
outside.
del E, it's actually, huh?
P dot del, that will be a bracket. E will be
Yeah.
outside.
Actually, this is not correct. Yeah, this is not correct. It's P dot del. So it's actually QEX. Okay. So it's essentially P dot del E. This is what is correct. Because force has to be a scalar, of course. So yeah. So basically, what you do here is you just write this as EX del X. Acha, what did I write here? One moment. This is. Yeah, this is not, this is L, this is not EX, this is LX, right? LX. And of course, the higher order are all neglected. So this is fine. Yeah. So Q, this is, yeah. This is absolutely fine, I guess. Yeah. So similarly, if you write down the torque, one can just write down the torque as well, which is basically just torque is, L by 2 cross F plus minus L by 2 cross F minus, all are vectors. So that basically means that you have, yeah, so this is again some very simple algebra. So just Q L by 2 cross, E of R plus L plus this L by 2 cross E plus L, all that does. And so if you just do a bit of jugglery here, so what you will find in this book is that you just add and subtract an E and all. And so basically you can see that if so this part, so here I can just just add an E and subtract an E. So this becomes, so this plus is quite clear, right? Because this is minus QE, so this becomes plus. Okay, so what one can do is that you just write this as QL by 2 cross E of R plus L plus, yes, maybe I should take this L by 2 outside, it's better. QL by 2 cross this thing plus E at the moment is what you have. So I do the plus ER and minus of ER. And the moment you do that, what you see is QL by 2 cross this E of R plus L minus of E of R plus twice E of R. This is already there. This is here, this. So you basically get yeah, so this part is known. So you basically get L by 2 cross P dot del E of R, and this is basically this is so yeah, so this is just P cross E. L by 2 cross P this thing plus P cross plus so with this is 2R, no? So this L by 2 and this one cancels out. So QL is P. So you just have P cross E, right? So finally this becomes your yeah. So this is my, yeah, this is the no, this final thing is just if I look at all three, then this is P cross E plus R cross P dot del E. Okay, this is the final expression. Okay, so these are fine. So these are just this thing. The what we are concerned with is this one, where this is this P dot del E. This is the one that we really care about. So from here we will just go to the next part, that is finding the expressions for this gradient and so essentially what we have is if you have a force on a moving dipole, and why this is important is that when you finally trap particles, remember that they are immersed typically in a fluid, right? So there's going to be a Brownian motion, so they're going to diffuse around. So in particles in air or water or whatever you're trapping in, they are generally diffusing around. So what you need to understand is that these are actually moving things that you've got to take up. So you know that the force on a moving charge, that is just nothing but QE plus essentially V cross B, right? Because moving matlab you have to consider this magnetic field and all. So this is V is essentially nothing but dx dt or whatever, dx dt or whichever direction is going as. So that means for dipole, what you will have is just this P dot del E plus dp dt cross B. Okay. So now generally for when we look at microscopic polarization, for very small particles, then we typically, so this P that I have written here, that we have so by the way, that first thing, that was essentially a Lorentz force, nothing but the Lorentz force, what we wrote, right? Now, if I have a particle having some kind of a macroscopic polarization, so this, yeah, I should just write down. This is nothing but the Lorentz force. And for macroscopic polarization, we basically have, so I should maybe put this as small p. This is just, yeah. What we typically have this as this force as P dot del E plus d p dt cross B. And so here is where the, our understanding comes. So this we have already seen is that, so the induced dipole, so that is very important to note that particles do not have a permanent dipole moment. This is extremely important to assume. This is very important to assume. Okay. So what we have, so when light is incident, essentially a dipole moment is induced, and that that basically goes as you have a polarizability. So that essentially is that that is electric field, say, that is induced, as this, right, where omega is the frequency of light, right? So that means I can just take this thing here. This is the macroscopic polarization polarizability, and I can just replace this here. Then what I get is this F is nothing but alpha E dot del E plus d dt cross B, right? Okay, so now we use one of these vector identities, and what we say is that, we use this identity that this E dot del E is del of E square by 2 minus E cross del cross E. We use this identity. Okay. Now this del cross E, is minus dB dt from our Maxwell's equations, and so that means I will basically have this, that your F becomes half of del of E square plus ddt of E cross B. So what is your E cross B?
Pointing vector.
Exactly. So this is nothing but the pointing vector. So this one, guys, so this is like, we typically write this as ds dt. So this is varying at, this is like typically the variation is at the frequency of light. Like this is 10 to the power 14 hertz typically for visible light. Okay, that is like omega level, it's varying. And measurement times in optical traps is much lesser. I mean, very, very advanced techniques. I mean, 10 to the 14, you do not get any detectors at the moment anyway. Okay. So maximum that is known is about nanosecond. That is the best that is in the class. We typically use of maximum, the detection speed or something. We go to around, like, best we have had is about 10 nanoseconds or 100 nanoseconds, that level. So this is varying at light frequency. So for measurement times used, microsecond to, I should change this, used, that is megahertz to gigahertz ds dt can be safely said to be 0, right? So basically we come to that f is half of del of e square. Acha, so one important thing is that this is e square, which is not, however, it's not e star. Okay, this is e square, right? And now if I say that your e is something like e0 e to the minus I phi, your e square is essentially e0 square e to the minus 2 I phi. Okay, so what then we do is, now you just take this, and you know that your alpha is some alpha dash plus I alpha double dash, where this is the real part, this is imaginary part, this is for propagation, and this is basically for your dissipation, you know, imaginary part of the polarizability. So finally, if I take the time average of the force here, what you will get, so essentially, by the way, this is 0 only when I take the time average, right? So this is, I'm saying that this average is 0. This is basically 0. This is not 0, so this is 0. Okay. So no, this part I should not write. This is not correct. This is not correct. This is 0. So this finally becomes some half of real part of alpha plus I alpha dash plus double dashed del of E0 square to the minus 2 I phi. And this one is this, right? So this basically becomes clearly, if I just do parts ka, so this is like half of real part alpha dash plus I alpha double dashed, तुम्हारा ये है e to the minus 2 I phi del of E0 square minus 2I E0 square del phi, right? So obviously then if I take the real now, so तुम्हारा एक, so if I do this time average, I should basically do real part of this and this whole thing is a time average. So if I do a time average here, तुम्हारा, so e to the 2I phi का time average क्या है? To इसका
0.
no, but this is no. This is, you have to do cos phi, na? Cos 2 phi, right? This cos 2 phi plus I sin 2 phi, right? So basically, it is time average of this, which means this is basically time average of 2 cos square phi, right? So 2 cos square phi average is 1, no? Half,
Half.
right? Right? So essentially, what I will get is, so then this is this is 1. So if I do this, I will basically get तुम्हारा ये गया, so you are going to get the real part. So ये imaginary I alpha इसके साथ गया and real part इसके साथ गया, right? So you will finally get alpha dash. अच्छा, this 2 2 alpha dash by 4 आता है anyway, so 2 का square. Anyway, so why is that 4 coming? So the expression typically is the alpha
So
dash
we
by
have a
4.
half outside, right, with real part of
Yeah. Okay, yeah. That's right, correct. So yes, that is 1/4, right? So this plus alpha double dashed by 2 E0 square del phi. So this guys, is clearly a gradient force, and this, as you can see, this is so clearly this is with the real part of the refractive. I mean, this is polarizability finally linked with the refractive index. This is with the imaginary part, which is the dissipation thing, and this is called this you can see is a phase gradient, and so this is intensity very clearly. This is a term gradient force, which is basically this is the dependent on the intensity gradient, and this is the phase gradient, and this is essentially a dissipative. Very clearly it's a dissipative force, because as you can see that it is associated with the imaginary part, which is there with absorption or dissipation or whatever, and this is a scattering force. Okay, and this is clearly a, as I said, this is a gradient force, and this causes trapping, and this destabilizes. So why does this cause trapping? Very clearly, you can see that if I choose my intensity, or this I, or if I have this I as some I0 e to the minus r square by omega square, right? Then very clearly, if I take delta of delta of I will get a minus this proportional to minus r, right? And that straight tells you that this implies that the f gradient is minus some k constant r. And what is this nature telling you finally?
Trapping,
Restoring force, right? So this
restoring
is
force. Yeah.
clearly a restoring force. And you can also very easily understand, guys, that Gaussian का तुम्हारा ऐसा होता है. If you take Gaussian ऐसा typically आता है. If you take the derivative, वो आएगा ऐसा type का, right? So you can see that at this part, the center, this is 0, and this part is the linear part, where I basically get this kind of thing working nicely. So this is the linear region of an optical trap. So it tells you that if I basically operate, so if I now try to find out the trapping potential, I will not go into, because I think Anisha's, I'm basically giving her presentation then, that's not fair. The trapping potential looks like this, and that essentially means that and that is quite easy. That is very obvious actually, because if your force is minus kx, then obviously the potential is half kx squared. So then you know that what this means is I cannot really go too far from the center of the trap. So at these regions and all, the force actually is not linear. It is non-linear. These parts are not. The gradient does not. It is not a simple expression, right? So it is only near this central part of the trap, central region of the trap, that you have a linear restoring force. Okay, the other parts it is not. So what is therefore crucial is that when you trap a particle, so when you actually more importantly, if you are trying to sort of move a particle, then you cannot really move with very, very large amplitudes, because that comes at the risk of sort of jolting the particle to nonlinear regions, these regions of the optical trap, which will be, where things become much more complicated. Okay, so this is lying at the heart of optical trapping, where you are clearly seeing that because you have a dipole force, the dipole forces can be split into a gradient force and a scattering force. The scattering force is very clearly also a radiation pressure force, and that is something which actually is in the direction of the beam. So that tries to push the particle out of the trap, whereas the gradient force is something which will try to, especially when you have expressions, when you have the intensity of this kind of a nature, then it will really have some linear restoring force, which essentially implies trapping. Okay. So this is a very vast subject, as you can obviously understand. So tell me, what questions are coming to your mind? So I don't want to go too much beyond this because it is not, yeah, that's because we are going to have a talk on this. But what questions are coming in mind?
So how
Any
does
questions
the,
coming?
like, depending on the power of the laser, there should be some difference in the trapping, right?
हाँ तो तुम्हारा ये है ना, so intense, so you can clearly see that it depends on the gradient of the intensity, right? So intensity क्या है? Intensity is nothing but powered by area, no? So powered बढ़ाओ क्या है? So that is, now you should appreciate what I was telling you, right? So remember in our diagram, so maybe I should go back to the diagram. Now you guys know what it means to trap. Where is it? बाप रे इतना नीचे था क्या? हाँ ये. So now you think of, oh, sorry. Yeah. Now you see, there are two ways I can increase intensity, right? So that is now you should understand what I was really implying when I said I need this arrangement. Why? Because I need to increase the beam size so that this input diameter of the beam is maximum. So it should basically fill up the back aperture of this objective. So have you guys seen microscope objectives? I'm sure you've seen, right? Somewhere now you get these toy objectives as well. Like for $1,000 you can buy a pretty good microscope system on Amazon. Anyway, so you should buy. If you haven't, please look at things like this. And so the objective, any microscope objective has a back aperture and a front aperture. So the beam that you finally couple into the trap, that has to be as big, because we have studied that the diameter output after you focus a Gaussian beam through a lens, the waist diameter essentially depends on the inverse of the input diameter, right? So the bigger the diameter, the smaller the waist. Smaller the waist money, powered by area, smaller the area, which means intensity is high. If you increase power, obviously that means that you're linearly increasing the intensity, and therefore the so-called trapping stiffness, as we say, that goes linearly with power. So that's a very important calibration strategy for optical traps, in order to see that you are, the system is working in ways that you sort of expect it to. And that comes when you actually increase the power of the laser, and you see that the trapping force or stiffness increases linearly. Okay, what else? What else are you thinking? Any other questions come to
Sir,
mind?
so if the spot size is small, we take the lens such that it covers the whole micro.
Aperture. Right, correct. So basically these two are crucial here, these two and these two.
But isn't that if the smaller the waist of the Gaussian, we get better intensity?
Yeah, so I increase the input diameter, na?
Okay.
Increase the input diameter, you get a smaller output diameter, no?
Okay.
It's lambda f by pi d, na?
Yes.
So that also you can say that तुम्हारा lambda जितना छोटा होगा, उतना तुम्हारा वो waist size भी छोटा होगा. So the larger intensities also you get.
Yes.
Okay. तो क्या और क्या सोच रहा है बोलो? I mean, this is a very vast topic, but generally first thoughts क्या है? Any other thoughts?
So intensity, if we increase, then it can also heat up the particle, no?
Absolutely correct. That is a dangerous thing, So Ashkin got the Nobel Prize in 2018 for optical traps. By the way, one thing I should tell you, you know what journal he published? Where that seminal paper where he first showed trapping of these glass, silica beads. I think 3 micron or 5 micron silica beads using a 532 nanometer light. That was the first instance of trapping, confining using light. Though there were thoughts about this, that you could actually, use radiation pressure forces and, light pressure or light forces to trap. So that was something that people even thought in the 1970s, but the first demonstration came by Arthur Ashkin in 1986. And the journal, obviously, you would think that it has to be, Physical Review Letters, which is the like the god journal of physics, but it was not. The journal he published was Optics Letters. Okay, and there are like about, I think, more than now by now I don't know, but a year back that paper had about 10,000 citations, or probably even more. Okay, so that tells you that it doesn't really matter that you have to publish in very, very so-called high impact factor journals. Finally, it is the quality of the work which really stands out, and just this journal, jargon, now nomenclature and big names are actually very, very spurious. Yeah. So yeah, but I was coming to that heating. So now what happens is, so yeah, I was saying that the Nobel Prize of Ashkin was what got was in demonstration of tweezers in biology. Now that is actually where this heating is the biggest issue, because remember, you can actually work with in principle you can work in vitro, in vivo, inside body also you can work, provided you're working with wavelengths which can penetrate the human skin. So people have thought of, drug delivery and all. You have these nanoparticles which, which can be attached to these biomolecules, and you guide them along veins and all. But I can assure you that those are all thoughts. I mean, nothing of that of real, importance has been achieved. I mean, it's not been demonstrated, but there are lots and lots of in vitro experiments that have been done with tweezers. Single DNA molecules have been caught and stretched, and all kinds of things have been done with them, which is remarkable. Cells also have been. We have trapped both. We have trapped both DNA as well as cells in our lab, and there it is a problem. So, for example, I remember a long time back, it was when you guys were still in school. We had a lab at JC Bose. So we were working with TKS. So TKS of biology, no? So he gave us some cancer cells. So we were trying to see if cancer white blood cells. Okay, so we were trying to see if these cancerous cells and normal cells behave differently in the trap. So what we saw was that if you just trap those cells, they were very easy to trap. If you trap those cells, they would sometime afterwards they would just bloat up like balloons. Okay, so we had no idea why that was happening, but it was very strange. It would just become very large suddenly. So that is a very, very crucial thing. So any kind of heat happens, for biological specimen. So that is the reason also why typically 1064 nanometers or 1064 nanometers is chosen as a trapping wavelength, because that is a wavelength where biological species do not absorb. So anything that absorbs is dangerous, because that scattering force thing that we have, alpha double dash, that keeps on increasing. So the gradient force becomes weak, in the sense the total force, gradient force component becomes weak, and also the cells get damaged. That is and the same reason metal nanoparticles are notoriously, metal particles, I would say, mesoscopic particles, are very difficult to trap, because again they have a finite absorptivity. So the bigger the particle, the more the absorption. So if you try to increase the power, what happens is the particles get hot, and the moment they get hot, they jiggle wildly around in the trap, and they just get out of the trap. So I think the largest particles that have been trapped, metallic particles, I think of the order of less than a micron, I guess. Even a micron sized particle has not been trapped successfully using tweezers, because they tend to become extremely hot.
Sir, but if we introduce some dissipative force like inside the liquid itself,
Dissipative force and cooling, you're saying?
either cooling or like some way to reduce their energy.
एनर्जी नहीं, वो तो पावर एब्सॉर्ब करेगा ना उसको. हाउ विल यू स्टॉप? Unless you have a active way of cooling the, so that actually people
Sir, I think
who
he's
do,
saying like a viscous liquid.
no, that
Some
is the anyway
frictional
done.
force. Some frictional force.
Viscous, you need a refrigerant or something, coolant. Viscous. Acha, this is, you're going into nitty-gritty. So I can assure you that if you have a high viscosity fluid, this becomes very, very difficult to trap, very difficult to move. And that you can envisage, because if you have very, so what a high viscosity liquid fluid does is that it will try to prevent the particle from sort of moving, right? Because friction is very high. Viscosity is nothing but friction, liquid friction, right? So high viscosity fluids, it is easier to trap because particle anyway is not, undergoing too much of Brownian motion. But it is one hell of a job trying to manipulate them, because the fluid is so resistant that you cannot absolutely, think of, it's very difficult. So high viscosity fluids are typically, and most importantly, remember that if the fluid itself is not transparent, then there's a huge problem, because that will, destroy the optical mode. It will itself absorb. So all kinds of things happen. So you need a transparent fluid. That is very important. And at the same time, if it is high viscosity, it's a big problem.
Sir, and what's the typical waist size of the beam in your lab?
Lambda, smallest. Lambda divided by NA. So I can tell you what we had in the lab with 1064. We measured about a micron, less than a micron, just about a micron. See, Anirudh, you try to get to the lowest because you will obviously want the highest possible gradient. And there are some fantastic effects that you get. And that, of course, since we are talking, let us just discuss it. So you remember we discussed this. So one of the most basic experiments you can do with optical tweezers, which unfortunately not too many groups in the world do, we do it quite a bit, is that, so you remember we discussed so much that if you start confining or focusing a beam very hard, this picture that I drew, this thing here. So this thing here, right? If I increase the angle a lot, then what happens is this beam turns a lot, right? So that completely destroys your paraxial approximation, because now this thing is so large and the beam diverges so much that the variation in x and y are similar almost to the variation in z. You cannot use the paraxial, you cannot drop that del square E del Z square term anymore, because there is also a way, so that equation is useless for optical traps with high numerical aperture objectives, and you see a very large Z component, extremely large Z component, and that leads to some very interesting things. So the moment you have a large Z component, remember that my pointing vector, which I always assume to be longitudinal, right? Because it's E cross B, and electric field I always say is transverse. So the pointing vector is always, that's why we say, right, it's in the direction of energy flow. It's in the direction of the K vector. But we saw that, of course, when you go to anisotropic media, then that changes, and you have a ray vector, you have a wave vector, and all that kind of stuff. It is no longer in the direction of K. But here it is even more interesting, because here you do not have it. It is clearly, because you have a very large Z component, there also is a pretty, I will say substantial, but a pretty largish transverse component of the pointing vector, which is in the direction of XY. And that creates all kinds of very interesting things. There is something called the spin Hall effect of light, which we have seen beautifully now. I think somebody is covering that. So I hope they will also cover that in tight focusing. So this pointing vector in the Z, the Z transverse component of the pointing vector causes extremely interesting things, both in the intensity distribution of the light, and also because when you actually have different circular polarizations, that causes some very nice effects. So, the intensity changes. Actually, what happens is you come with, say, RCP, that is right circularly polarized light. You actually will get a component of left circularly polarized light as well. there is this typical thing called spin to orbit conversion. So that will be covered by Nirmal formally in that atomic optical physics course that we do next year, next semester. Okay, but this is something that our group has now really looked in very deeply, the spin to orbit conversion of light in optical tweezers, for with which we have done it with. So now what we are doing it is using these higher order beams, so Hermite Gaussian beams. With Hermite Gaussian beams, circularly polarized Hermite Gaussian beams, you get very, very interesting effects. So you actually get this thing called orbital Hall effect, and very nice stuff happens. But as you can envisage, this is something which is dealing with the very basic properties of light itself, and only optical tweezers facilitates this, because of this very tight focusing of light, that looks at the very basic tenets of wave optics. Okay, so that is a very fascinating thing that we do. Okay, so yeah, there are all kinds of things you can do. Statistical mechanics, this is a absolute the haven of experiments that can be done. Also, as I said, such tight focusing enables some very interesting stuff that you can do in basic spin orbit interaction of light and all those sort of things. Okay, tell me, any other thing? I mean, there are millions of things you can probably think of, but yeah, at the moment. Okay, so if you don't have any questions right now, let us then stop sharing this. And where is the link? Yes, stop presenting. Yeah, so I think you guys have got your routine, right?
Yes, sir.
Yes.
Yeah, so now I think Fatafat, you decide the Viva schedule. Vishwajit, please work with them. Presentations, as we said, 15 to 18, then Viva should be finished before that. Okay, so please work with Vishwajit. Maybe you guys draw up a schedule yourselves, send it to Vishwajit.
Rohan told na he will share
I'll
a
yes, I'll create a Google form
Kardo.
and collect dates on which
Yeah,
to do that.
Please do that. Please do that, and don't keep day times at like. I would prefer in the afternoon, but maybe 11:30. Well, my kids have school till 12, so that is sort of an issue. But anyway, that's okay. People who want to
So
do at 11 is also fine.
around after 12 p.m.
That is perfect. That will be ideal, but it's okay. We can do at 11 o'clock as well. 11:30 as well.
Okay.
Keep some lunchtime there. Some 2 to 3 should be some lunchtime for me, and then after that is absolutely fine. Anytime.
Okay, sir.
And sir, we also need to be there.
I think it's useful if you are there. It
Okay,
may be
sir.
useful. I think it's useful if you are there, right? Because yeah, they will have some encouragement as well.
Encourage.
Yeah. Anyway, okay. So what? Any other stuff? And acha, so I was thinking that maybe we should do a session on presentations. Is it necessary? I mean, presentations are some tips I will tell you in the sense that do not see, there are some basic tips and ground rules in PowerPoint presentations. One is that you should absolutely ensure that you have font sizes more than 28 or 30. Don't go below that. I mean, of course, here it's on computer, I can see anything, but make these habits. Yeah, finally, the world will not be online. Sorry? Sorry? Yeah? Okay. Anyway, so please ensure that the font sizes, make it a habit, because once the world reopens and you will actually present in physically somewhere, tiny fonts and all are horrible, horrible. I'll tell you, because people just stop reading. You try to read for 5 minutes, you fail, then you switch off and go to sleep. Okay, so never do that. Don't overfill slides. Don't write a paper in a slide. No, never. Use 5 slides. What your content in a slide has to be mostly in the form of bullets and basic information. Maybe use telegraphic language, but whatever you want to present has to be what you want to convey, the important points. That has to be there. Absolutely has to be there. Expand on them. Don't put the expanded, never read from your slides. That is again very bad presentation practice. Reading, I can also do, right? We are not illiterate. I mean, if you stand there and read from a slide, why are you there, right? You just put the slide and disappear. So that is not absolutely what should be done. You should know what the contents are and speak directly to the audience. Of course, now it's online and all, but the slide quality should not change. That should be the same. Okay. If you use abbreviations, please expand them. Never just put abbreviations and think that the whole world knows it. No, never. They don't. Okay. And another very, 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 very important thing, whatever you put in the slide, you have to know. You have to know. You put on the slide and you cannot defend it. That is the worst thing that can happen. If you don't know something, don't put it. If you know something and somebody asks you a question, you blabber, people think that you're an idiot. Never do that. If you don't understand, don't put it. If you understand, you know it. I'm sorry, if you put it, you know it. So that is another very important thing. And again, another crucial thing is, don't assume that people who are, you're listening to you, they know the thing already. The assumption should be they know nothing. So, however, you have a finite amount of time, right? So if you go into details, that's going to be a complete waste of time because you're not going to cover what the thing is actually all about. So details only come when you ask questions. The big picture is what is crucial. Okay, so when you are presenting the papers, present the big picture, the basic understanding. Details are 5 slides maximum. The important part is to check whether you have understood the phenomena that you're talking about. Okay, but crucial, and don't use animations are very good, but overuse of animations makes it ridiculous actually. Okay, it makes it the whole thing like a cheap Bollywood film or something. Don't do it. Animations should be there for effect, but you should not have letters which come dancing in every time and things like that. Doesn't make any sense. What you should have is animations for emphasis, and also do not use striking very high contrast, or actually more important than that is never put yellow on white or pink, or light pink on white, or deep blue on black, because people again cannot read. Use contrast colors, but not garish colors. That is also very important. Okay, I know many of you prefer LaTeX, slides by PDF that way, but I myself don't prefer that because animations are probably difficult to get through that, and animations used judiciously are very, very, very useful. I mean, they can really create a difference in your audience if you can use animations properly. Okay, the emphasis part, the drama part is really very, very good, but it should not be overdone. Okay, and of course, I think the report I told you, overleaf, APS already has overleaf has the APS format. It's very simple to use. Please use that, and yeah, write properly, use proper figures, and just do it. Okay, so yeah, that is the end of the course that way. So it's been a very for me second time, but again, as usual, I have learned quite a bit, and I think your class, though, I'm keeping on teaching, I think, forever. Again, next semester we'll meet, some of us. So I would also like that some of you write and tell me how the course went. I'm not asking for a formal presentation that we did last time because that was something that I wanted to know to improve. Now, of course, the course is done. Maybe I'll teach this course again once more. But yeah, if you have feedback, please write me email about what you liked and what you did not like. Okay. Okay, if there are any more questions, if there aren't any more questions, let us call it a day. Thanks. It's been a good journey and hopefully give good presentations. Yeah.
Thank you, sir.
Anybody else? Any?
Sir, Hitesh wrote something in the chat.
Oh, okay. Thank you, Hitesh. Yeah, you guys are brilliant. So I hope that you will also be a part of the next course, some of you at least, because I really enjoy discussing with you. And I think I have learned a lot, tremendously, because
So
I,
next course is
yeah,
in which one?
optical and atomic physics.
Haha. Yes,
Okay,
I'll get that.
so that one we will do this. So that I personally think Nirmala's part will be more interesting. My part will be so, but then there also I will try to keep. I mean, see, what I'll be doing is not really MSc. You're like second, okay, first year. Yeah, that is probably okay. But my thing will be that I will look at. I mean, laser cooling is something that you guys should know, and that part I will really try to get it into. So again, this is. I mean, the experiment that I'm going to take up is I'm already telling you. Okay. Thanks, Anirudh. Yeah, but I will tell you that I will. So just like we did optical, see this one, I will tell you it took me a lot of time to come up with this scheme of, because now I've decided that whatever course I'm going to teach in physics in my life, I'm going to take up a practical demo. I mean, I'm going to start from the last chapter of the page. I mean, last chapter of the book, because otherwise I myself don't know why any student would find things interesting. I will, as a rule, I will start from things that you do not know and which will basically, uh, you know, be fascinating. And then we will, unveil every step one by one. That is what I'm going to do. This course, it was so diverse, it was difficult for me. For the next course semester, it's trivial because I'm just going to tell you that we're going to learn laser cooling atoms. That basically is everything in atomic physics that you can think of. Absolutely clear. I'm already telling you. And that is something fascinating. See, guys, 2 Nobel Prizes, fourth one within 5 years of the experiment being done. That is probably a world record. I mean, the whole field of atomic spectroscopy, I'm going to repeat this again when I'm starting the course, but I can't resist, absolutely has been driven by experiments completely. Okay. So that is something very nice. And it's a pity that it was not taught in ISA, but you guys, that way at least you will learn some atomic physics. But yeah, okay.